interconnection network, right? Or a simple bus, right, is sufficient to connect these components, right? But today we're designing parallel computers, right? And chips are composed of mainly two components. The parallel computers, we have the processors plus the interconnection networks, or the chip multiprocessors. So for example, the multi-cores or GPUs, right? We have many cores in the same chip, right? And which are connected by the network on chip. And we definitely have some accelerator design to support some emergent applications, such as the machine learning or other applications, right? And we have some simple processors plus the interconnection networks. Right? So interconnection network is a broad word for covering both parallel computer and chip multiprocessors. So network on chip only refers to the interconnection network that connects some components in the same chip, right? So they have similar definition, but the NoC, the network on chip, may have a narrow scope. Okay. So the communication within the parallel computing system is much more expensive and determining factor for every aspect of the system. Right? Why? Because assume we have sufficient cores or the computation resources, right? But if we cannot, we do not have an ideal communication fabrics, so which means we cannot deliver the data to the processing units in time. So this can cause some delays in the computation, right? Just imagine that if we have lots of the traffic congestions, right, on the road, so what can happen? So lots of the people will be, will be late for their work or no matter other things, right? Because they will stuck at the road, on the road, right? So the communication, so that communication dominates the performance, right, energy consumption, and usability of the system and cost of overall system. Right? That's the reason why we need to learn some concepts in the interconnection networks. Okay. So what is an interconnection network? So an interconnection network is a fabric that is responsible for fast, reliable communication among the processing elements, the memory modules, the input-output units of a parallel computer or a multi-core chip. Right? We have learned how to build a processing elements, right? So which refers to a microarchitecture for the processor, right? So which consists of registers, pipeline, ALU, right, and some private, some cache, right? And then we have some memory modules, which means different levels of the caches, right? L1 cache, shared cache, right? All these should be connected by the interconnection network, right, to compose a whole system, right? And the interconnection network is composed of hardware, both hardware and software entities. On the hardware side, it contains the routers, the switching elements, the buffers, control units, and the communication links in the form of a network topology. So just imagine that, right? So if you are connected to the Wi-Fi, so which is supported by what? A router at home, right? Same thing for the on-chip communication fabrics. We also need some routers or switching elements, right, to process or regulate the communication traffics, right? And we have buffers to store these packets, right? And definitely we have to implement some control logics, right? And definitely we have some communication links, a bundle of wires somehow. On the software side, it contains the routing algorithm and flow control protocols. So what does the routing algorithm mean? So we need to decide how to route the packets through the interconnection networks, right? And the flow control, how do we regulate the communication? What kind of policy should be implemented or deployed to regulate these packets across the network, right? This is the flow control. Is that clear? One question for, okay, it works, okay. So what is multiprocessor or multi-core architecture? Right, so on-chip interconnects, or another name is network-on-chip, is for the multi-core processor. Right? So off-chip interconnects is clusters of servers. If we have a data center, right, different individual computers should be connected with bundle of what? The cables, right? For the chip, it's wires, a bundle of wires. Right? That's the differences between the interconnects for the multiprocessor or the multi-core architectures. Is that clear? So they are using different kind of fabrics to connect these components, right? And we do also have different kinds of the challenges for designing these different kinds of interconnects. For example, data center, right? We have lots of probably thousands of 10,000s of the computers that should be connected, right? So the scalability should be the issue. How do we design an interconnection network to connect the large number of the servers or the computers using a limited number of the cables, right? This is a problem. So for two computers, it's quite easy. One cable can solve the problem. But what if you have lots of the computers? How do we solve that? For on-chip interconnects, definitely we have much less number of the much fewer number of the cores, right? For today, processor we only have 8 cores, 16 cores, or 100 cores. So the challenge will be different. But the thing is, we have very limited number of the wires, right? And how can we utilize this limited number of the wires to connect these tens or hundreds of cores on a single chip, right? So an example of the parallel computer architecture. So in this course, we mainly focus on the on-chip interconnects, right? Rather than the off-chip interconnects. Right? So example of a parallel architecture is shared memory module, right? So basically, the different memory distributed among processors, right? And the processors are connected via direct switch or non-direct switch interconnection networks. So we will explain this later. So communication takes place through the shared memory read and write from the shared memory locations. Do you remember that? If we have the shared memory system, right? So these memory modules are distributed, right, across the chip, right? And the communications is happening everywhere. So that's the reason why we need to implement an interconnection network to provide each core the capability of accessing remote memory modules. Is that correct? Or even further, if later, so we have what? The shared cache, right? We have different kinds of the coherence traffic, right? Should be communicated through the interconnection networks, right? So if you have delay in that, which means what? This will further increase your miss penalty. Am I right? If you cannot find a data in your local in your register, right? So you probably need to fetch the data from the memory, right? Any delays in the interconnection network will pose additional latency for fetching the data. Am I right? So this will increase your what? The miss penalty. Right? So that's the reason why I said the interconnection network is a critical part of today's process design, right? And it mainly determines the overall system performance. Is that clear? And also the multiprocessor computer distributed system, right? So this is another one. We mentioned that we have the on-chip and off-chip. And this is for the off-chip. A multi-processor, multi-computer with 16 CPUs, each it has its own private memory. And the bitmap or image of split up among 16 memories. The process communicates through explicitly message sent and received. So what does it mean? They are not sharing the same memory system. Am I right? So which means each processor cannot access others' memories. Am I right? So in such a case, we only have to communicate with through explicit message, send and receive. So more specifically, we send a request, right, for fetching a given copy of the data, and then we will send back the data to the requester, right? So this is different than the previous one, but they have the same thing. It's the interconnection network, right? But with different communication patterns, right? And different challenges and constraints, and even for the physical fabrics, they are different, right? Is that clear? And this schematic of the parallel computer is same thing. We have all of these processor and memory modules are connected by the interconnection network. This is the key, right? That's why I mentioned. We have the computation units, we have storage, right? So the interconnection network is the bridge between the computation unit and the storage, right? Because we need to move the data around the chip for the computation, right? For the parallel computing, right? If you say, okay, only one core is sufficient, or probably you can just get rid of the interconnection network, right? One core is sufficient. But if we have multi-cores and many memory modules, we should, right, use the interconnection network to connect these components as a whole system. So this is a critical part of that. So the types of the interconnection networks, in summary, right, we have processor to memory, different kinds of configurations. We have we have distributed or unified memory. So how to connect the processor to memory and the processor to processor, right? And I/O, right, used to connect I/O devices with the processor memories. And control plane interconnect networks used to carry the control signals, especially for large-scale supercomputers. And these are in addition to the data interconnection network. Sometimes they separate the interconnection network for different kinds of purpose, right? We implement a dedicated interconnection network for the data, right? And we implement a dedicated interconnection network for the control. Why? Because usually the control signal or message is much shorter or smaller than the data, right? So one request probably can, initiate like a bulk of the data, the transfer of a large amount of the data, right? So this will result in different kinds of requirements for the interconnection networks. So which means if we use our high bandwidth interconnection network to transfer the control message, probably it's kind of underutilize the resource, right? So probably we can design a dedicated, lightweight interconnection network for the control, right? And high bandwidth interconnection network for the data transfer. That's clear. Sometimes people adopt this kind of design. And network components, okay, network components. So we have network interface. So the communication between a node and the network. Why? Because we need to prepare some messages, or the network interface is responsible for receiving and decoding the message that's sent by the other nodes, right? Is that clear? And the link bundle of the wires and the fibers that carry the signals, right? And the switches connects a fixed number of input channels to a fixed number of output channels. And in this community, switches may also have the router functions and the use of word routers. Is that clear? 3 key components, right, in the network. Basically, network interface is responsible for receiving and sending the message to the network, right? And the link switches. And the interconnection network basics, okay, there are multiple things that we need to learn probably in the following lectures. Usually these concepts or basics usually will be discussed in 3 or 4 lectures. I think it's probably too much. So at this stage, we only need to go over some basic concepts of these terminologies, and the only requirement is just to understand. So what is the interconnection network? I think that's sufficient for you. So the first one is topology. Have you heard this word before? I believe most of you should should hear see this word before. So specify the way switches are wired, right? So daily example is how do we design the road connect different buildings, right? So this is topology. And once you design this kind of floor plan or road plan, so it will affect the routing, reliability, throughput, latency, and other things, many others, right? Because how many lanes you design for one road will determine what? The throughput, right? And which kind of roads are connected or built will affect the routing, right? So this is the fundamental of an interconnection network. And what is the routing? How does the message get from the source to the destination? Static or adaptive, right? So there are multiple selections for you, right? To commute from the university or the campus to your home, right? But which one is the best? And which route you should select? So this is the routing. Right? Somehow it will affect your throughput. Is that clear? So probably we can go over this later. And buffering and flow control. So what do we store within the network? The entire packet or parts of the packet, etc. So there are many things that we need to consider. So you may ask, why we need to buffer some messages, right? Why we need to buffer some messages? Right. This is because we need to process the data stage by stage, right? So you must have some buffer to store this data, right? At the intermediate stages, like what? Like the pipeline. Am I right? So imagine that. So what are the key components to achieve the pipeline? What kind of the hardware we implement between different stages? Do you remember that? Yes, the buffer, right? The latch to temporarily store some intermediate results, right? So the same thing, right? The same thing for the interconnection network. So we need to implement some storage, right? To temporarily store the packets during the transmission, right? To avoid some contentions or other things. Is that clear? So how do we throw during the oversubscription tightly coupled with routing strategy? Okay, so this should be done by the flow control, right? So for example, so if, right, so all the cars, right, are going to the same road, so what can happen? Congestion. So how can we avoid that? Right. So apparently, if there are 4 ways, there are 4 selections available for you, right, to select. So if all of us to select the same path, so probably we can cause what? The congestion. So probably in such case, probably we can, so probably 4 of us can select different ways to go, right? This can avoid the congestions. And this can be achieved by the flow control policies. Is that clear? So there are lots of the topologies. There are lots of topologies, right? So we have a tree, right? We have mesh, torus, hypercube, hierarchical ring, hex mesh. There are tons of the topology, right? That can provide to design the multi-core or processors, or even for the for the data centers. Right? But which one is the best, and how do we analyze the performance of these topologies? Right? This is the key. Am I right? Because if we have 5, 6 cores, so you are responsible for designing the interconnection network for this system, right? So usually we have several groups, several teams, right? One team is responsible for designing the processor, the microarchitecture, right? The process design, and another team is to design the memory system, right? So how many caches, what's the size for the register for the cache and for the memory system, right? What's the addressing mode for that, and the set associative, fully associative direct map. And then the third team is to what? So once the previous two teams, right, confirm their design, and the last team is to what? To select appropriate interconnection network to connect these components. And if you were given this task, so how do you select and design the topology? Hmm? Yes, you're right. Yeah, apparently you already got the key essence of this course, right? So we need to understand the requirements, right, of these components or from other teams, and then we can select appropriate interconnection network, right? So what should we consider, right? So the first one is regular or irregular topology, right? This is very important concept because the regular one probably is easy to scale. For irregular topology, it will give you hard time to scale out the entire interconnection network, right? And the routing distance, right? The second consideration. So number of links or hops along a route, right? So it's how far. Right? The second is the diameter. Diameter means the maximum routing distance within the network. And the following is the average distance. So the average number of the hop across all valid routes or routes. Right? So it pronounced like a route or route. Or it determines.
Depends on where you're from.
Oh, really?
Either one. Yeah.
Oh, I see. So, but all of you call this router, right? Right, but the routes or routes might be different. Oh, I see. Oh, interesting. So sometimes people say data, sometimes say data, right? So it also depends on where you're from, right? I see. And also we need to consider the bisection bandwidth, right? Often used to describe the network performance, right? So we will go over this kind of matrix later. Okay, so cut the net. Basically, the bisection bandwidth means we cut the network in half and sum the bandwidth of the link served. This is a very important thing. The last one is blocking or non-blocking. So if connecting any permutation of the source and destination is possible, the network is non-blocking. Otherwise, network is blocking. Right. So rearrangeable non-blocking summit. So okay, we will discuss this later because I think if it's just based on the description, it's hard to understand, right? So I mean, for all of these performance matrix, right? But we definitely need to consider this. Why? Because if you are using the Google Map, right, to give you an estimated arrival time, so usually probably you also need to consider what? The distance, right? So how many miles between your home and the campus, right? And also for designing the routing algorithm, we also need to consider the maximum routing distance. Why? Because it's not only one person, right? We need to consider all of the persons, right, across the entire chip, not only yourself. Right? That's the reason why we need to consider the maximum routing distance. Right? Why we should consider average is same thing. Right? The maximum routing distance is kind of what? The quality of service. Right? The quality of service. Right? We need to make a fair design for each people. Right? So average distance probably is after a kind of trade-off is the best solution for all of the people. Right? So diameter is the worst case, right? Is that clear? And the bisection bandwidth is what? You can understand is like how many rows or routes between the source and destination. I can provide you the best throughput. Okay. So the topology, okay, today we will go over some topologies together, okay. So for example, bus is the simplest one, point to point, right? Crossbar, ring, tree, omega, hypercube, mesh, torus, butterfly, and so many topologies, right? You have utilized this one, but you should be able to analyze these topologies using the matrix I mentioned before, right? So we will go over this matrix one by one, okay. So matrix, do you value that cost? Of course. The latency in hops. So in such case, we assume how many hops we have and contention and many others that you need to consider energy bandwidth over a system. But in general, right? So I mean, so if you were an expert in the interconnection network, so usually we just use the hop count. So how many hops, right? The diameter, the bisection bandwidth to analyze this, because the contention, right? The contention is usually determined by what? The specific application, right? If there is an event is happening, for example, is I think it's game day, probably UCF game day. So lots of people will be what? Will be coming to what? The campus. So definitely, there are lots of the traffic around the campus. Right? We will see lots of traffic car contention, right? Traffic congestions around the campus. That's because what? The specific application. Right? So if you are just given a topology, so it's hard to analyze the contention, right? You should also have an application, right? You run this application on a given topology, so you will analyze the contention each. Is that clear? But if you are just given a topology, so probably the only thing we can do is just to analyze the average hop. Am I right? The average hop, the diameter, and the bisection bandwidth. Right. So we'll do this later. So the first one, right? The first one is bus, right? So all nodes are connected to a single link. The good thing is it's quite simple and cost effective for a small number of nodes, and easy to implement the coherence, the snooping. Do you remember that? So what is snooping protocol? Yes. All these nodes, right, are listening and monitoring the activities happening on the bus. Right? So the bus is the best way to implement the snooping cache coherence. Right? But the problem is not scalable to large number of nodes because we have limited bandwidth. Right? So first of all, we need to check what is the bisection bandwidth. Bisection bandwidth if we cut the bus into two halves. So how many links we have across the middle line? So let me draw something. Cut here. So how many links we have? Only one, right? So which means the bisection bandwidth is just this link, one. Is that clear? So this is bisection bandwidth. We cut the entire network into two halves. And we count how many links across the middle. This right, only one. Right? So what is the diameter for this network? Which means the longest distance between any pair of the nodes. Right. Apparently, these two. This is the diameter. Right? The maximum number of hops between these two nodes, right? This is what the diameter, right? And second thing is what the average hop count. So you have to count all of them and divide it by number of the pairs, and you will get what? The average hop count, right? So you only have three things to analyze, right? The bisection bandwidth, number of hop counts, and the diameter, right? So why we said it's not scalable to large number of the nodes? because we have eight nodes here, right? The bisection bandwidth is only 1. No matter how many nodes you added to the interconnection network, bisection bandwidth is always 1, right? So in such a case, so each of these nodes will share very limited bandwidth. Am I right? And also scalability. Why? Because the diameter will be increased linearly. Right? For this one is 8. If you add one more node here, it's 9. Right? So it's not kind of a scalable way, right? If you have lots of nodes here. Right? The communication between the nodes will be very poor, and the bandwidth is the same thing. Right? For example, how to understand this problem is like kind of, you can imagine this is the number of cars on the road, and you only have one road. Right? So we definitely will have the congestions. The more cars we have, the more contention will happen. Right? Because we only have a very limited number of the roads, right? To accommodate all these nodes. Is that clear? So how do we solve that? So probably it is a good way to do. Let me clear my drawings. It is a better way to do that. So point to point. So every node is connected to the others, right? We have lowest contention and potential lowest latency, right? Because there's a dedicated connection between any pair of nodes, right? We won't have any contention issues because we have sufficient resources, right? To analyze this one, like mentioned, so what would be the diameter? 1, right? So the worst case for this connection, this type of topology is 1, right? How about the bisection bandwidth? Let's do again. So you basically just cut and count how many links across this line, right? There are lots of the connections, right? So which means the bisection bandwidth is much larger than the previous one. Do you know what I mean? So cut the entire network connection into two halves and to check how many lines across 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And to count how many links across this line, and you will get the bisection bandwidth, right? And the average hop count, of course, is 1, right? But the problem is we have the highest cost. There is always a trade-off, right? So remember that the essence of the key principle of the computer architecture is what? The trade-off, right? We have the best, right? We have the best latency. We have the best bisection bandwidth, but definitely we have the worst cost. Right? So is that clear? And definitely it's not a scalable way to do that because we are facing loss of the cost to implement such a network design. Basically, if you have n nodes, right? N nodes, this would require what? N connection at each node, right? And we have n square links. It's really hard to do that. If you have 1,000 computers, so which means each computer should have 1,000 port. It's impossible, right? And you have 1,000 square links, which means add 3 more 0. Right? So it's 1 million links. Right, so basically it's impossible to do that. right? So this is not a scalable way to implement point-to-point topology, right? So how about another one, crossbar? So crossbar is every node connected to every other with a shared link for each direction, enable concurrent transit to non-conflicting destinations. Could it be cost-effective for a smaller number of the nodes? So what does this mean? So we have kind of the communications course here. So for example, right? So what does probably non-block means? So let me do this one. So for example, 1 can go to 0, right? So 1 can go straight to 0, 2 can go to 1, 3 can go to 2. No blocking, right? Unless if 5 go to 5 and 4 wants to go to 5. Unfortunately, this has been utilized by another thing, so we have contention. So this is a crossbar design. And again, so what probably would be the diameter for this one, and what could be bisection bandwidth for this one? Same, cut the network into half, and to check how many links we have across this line. This is the bisection. And same thing is what's the hop count? To just count how many hops from 7 to 0. Or 7 to 7 is not the way, right? Because we won't send the message to ourselves. Right? That clear? And this is some common way used in some process design, right? Core to cache banks networks to guarantee the high throughput, low latency, but it's expensive because the cost is still n squared. Right.
Bisection is telling you what when you cut it. What ultimately you're getting out of bisection when you do that.
So bisection, you mean?
Yeah.
So cut the network into half.
Right. When you cut it in half, what are you trying to get to by cutting it in half? I mean, what are you trying to derive as a result of cutting it in half? Okay. So basically, which means so the reason why, right, we are cutting the network into half. This is because in some cases we need to count the communication, for example. So how many pair of the networks across the middle line, right? To say if there are lots of the communications, right? So you just imagine you connect any pair of the nodes, right? And then you cut into half. So you probably will see what the saturation point. Do you know what I mean? So this is not a good example. Probably I can grab another one to show that. Oh, sorry. Let me go to a simple example. So this is too complicated. For this one, okay. Let me share draw a line. So right. So if we connect any pair of the communication, for example, 0, 3, 4, 5, right? 6, 7. Then what do we do? Same thing, right? You basically connect lots of the things. And then you will see that is basically the middle point covers the most number of the communication patterns, right? So in such a case, we need to cut the network in the middle line and to see, so what is the bandwidth that I can provide it to cover all these kinds of the communication patterns. So you're just trying to find the biggest pipe. What's the biggest pipe?
Yes. So the middle line would be the bottleneck. Right. That's the reason why we need to cut the communication pattern into half. Right. So this is a much simpler example to show why we need to consider the bisection bandwidth. Right. Is that clear? And then, so another one is much simpler than that one. So it's ring, right? So as compared to so each node connect to exactly two other nodes from a continuous path, such the packets can reach any road, right? So it's cheap. But the problem is high latency, not easy to scale. Bisection bandwidth remain constant. Let's see what is the bisection bandwidth. So how do we do the bisection bandwidth? Cut into half, 2. It's a constant. So no matter how many nodes you add to the ring topologies, right? So your bisection bandwidth is still a constant, 2, right? It's not a scalable way to do that, right? So how about the diameter? So as compared to bus, right? So you add another direction to that. So probably it can reduce the diameter into half, right? Because usually the longest point in the bus is what? From 0 to 1, 0 to n, right? So you can basically go to another direction to reach to the end. So this won't be the longest path, right? So the longest path is the middle part to both ends, right? So this would be your diameter, right? So, but it's still, we have the high latency problem, right? But it's much cheap in cost, right? So in today's processors, Intel still uses, I think, the ring topology for 8-core processor, right? Because the diameter is 4, it's okay, right? The bisection bandwidth is fine, right? So usually, this is still the most popular topology for a 4-core or 8-core processors. But even for 64-core processors, they also utilize ring-like topologies. But this I can explain to you later. Okay. So you should know what is the state of art today. So can we do better than the ring topology? Right. So ring has 2 types of rings. The first one is unidirection ring, single direction pathway, a simple topology and implementation, right? But they also have 2 bidirectional rings. So which means the multi-directional pathway or multiple rings. So reduce the latency and further probably can improve the scalability a little bit, right? So if you have 16 cores, usually we do 1 direction, right? So at this stage, you can add 2 direction. What does 2 direction means? Let me draw something here. So usually you have a single direction ring, right? To connect 4, right? And right now you have bidirection. You still have 4 nodes. But we can either go this way or we can go this way. 2 wires. Right. Basically, you can consider this as 2 rings. Right? 2 rings to support 2 different directions, and 1 ring for only 1 direction. Right. So this can increase your bisection bandwidth, further increase your bisection bandwidth. Basically, double your bisection bandwidth. Is that clear? For this one, you cut in half 2, cut in half 4. Right. So these bidirectional rings have a better scalability as compared to a unidirectional ring. Am I right? So how about next one? Mesh topology. Right? Because we mentioned that the bisection bandwidth in the ring topology is still constant, but for the mesh topology, probably we can do better. Why? So what would be the bisection bandwidth for this one? Cut into half. How many links we have? We assume this is n by n topology. N nodes. So how many links we have? The bisection bandwidth should be n, right? 1, 2, 3, 4, 4. So the bisection bandwidth is n. It's not a constant, right? So it has a better scalability. Am I right? It has a better bisection because it has better bisection bandwidth. Right. And each node connects to different 4 directions, right? And it can provide more path diversity as compared to ring, because the ring direction can only go 2 ways, right? But for the mesh topology, each node you have 4 ways to go, so it provides more paths, right? So which means you have a better throughput, right? Because you have better choices in selecting the routes, right?
Just to guess, bidirectional for this one here, is that 8 if you're cutting it in half? If you count the number of lines you're slicing the root.
Yes. If it's bidirectional. So usually, right? So for this one, actually, it's just bidirectional, right? Because you have 2 ways to go, right? Because each core has 4 ways to select, right? And this one also have 4 ways to do. Right? So the combination of these 2 routers will naturally perform bidirectional link between these 2 pair of things. Right? But since you consider n is a variable, right? So the 2 constant can be ignored, because when you computing the complexity, from the algorithm course, if you have 2, so sometimes you can ignore the 2, right? And only take the n into consideration. Is that clear? Right. Right. So it's much easier for layout. And sometimes the high performance processor for 16 cores, they use this kind of design. But Intel, they didn't use the mesh topology, but they use kind of a ring topology. Let me explain that. You may have these kind of problems during the interview. Okay, so how did Intel design their mesh topology? Right, it's mesh-like topology, but not it's mesh. They utilize multiple rings. They implement the ring here, ring here, ring here, ring here, and a ring here. Right? They further increase the bandwidth and are reducing the diameter for each dimension. Right? So this is Intel's design with multiple rings, and they couple these kind of multiple rings together to form a mesh-like topology. Is that clear? This is Intel's design. It's good performance. And next one is Taurus, right? It's kind of Intel one. It's kind of Intel design, right? But there are some tiny differences, right? Because I think it's too. Let me draw this one. So if you can understand what I'm saying, so you just understand it. If you cannot understand, it's okay, right? So for a Taurus, right? Taurus, the switch. The difference is the switch. This switch will connect to multiple directions, right? Because in the mesh, usually the edge nodes, right, only connects to the here and here, right? So basically for this node, how many? We have 1, 2, 2 input, 2 output, right? And for the middle one, they have 4 connections. 4 connections, right? So which means this switch is 4 input and 4 output. So we can assume it's 4x4 switch, right? It's 4x4 switch, right? For Taurus, it's basically the same. The only difference is just for the edge routers, right? Probably this kind of routers will have 2 more ports, right? So basically all of these routers should have 4x4 switches. But for Intel design, they have 2 rings, right? So for ring, what is a switch? It's just one input port and one output port, right? One input and one output, right? If it's bidirectional, it's just two inputs, two output, right? And then for another direction, we also have 2x2 direction, right? But why the Intel one is better than 4x4? 4x4 is what? 16, right? 2x2 is 4 plus 4, so you have 8. So this is for the cost. So usually the cost for implementing the switch is just equal to the n by n. The cost is n squared, you can assume, right? So for this kind of design, actually, you only have 2, and so you have much. It's not 2n. So basically, you have right, you have a smaller cost. Is that clear? By decoupling the dimension. Right. Is that clear? So they have a smarter design for this one. Right. And I met, I met this author, the inventor for the Intel's the topology during the conference. He was the session chair for my presentation, and he discussed this kind of design with me. So it's quite interesting, right? So a very small change for the topology, right, which can result in tremendous of reductions in the cost. Right? Same, right? The same, the performance, but much less cost. Very interesting, right? So, and we also have the tree topology, right? The tree topology is basically you have multiple nodes and organized in a tree-like topology. Right? It's also easy to lay out, but the problem is how do we count the bisection bandwidth for this type of the topology? Have you realized this problem? If we just cut the topology like this, only one, right? But if cut this one, so we have a lot. So which one should we go? The answer is we should consider the worst case. Right? That's the reason why the root can be a bottleneck for here. Right? So there are different kinds of optimization have been done. So probably we can implement lots of links here, right? So that we can solve this problem. So we call this fat tree. Right? And if there is communication from the root to the leaf, so lots of the contention will happen here. Right? So this reason why, but it's good for the local. Right? Sometimes people will utilize the tree topology, sometimes not. It depends on what kinds of the applications that you will run on the chip, and you can select the topology accordingly. Right? Is that clear? And I think we can go to the next one. And there are two things that you need to be aware of. The first one is circuit switching. The second one is packet switching. I just remember the differences between this one. So the circuit switching is set up the full path before the transmission. Right? So establish the route, then send the data. Right? So this won't require any buffering. Right? Because the packet will directly go through the entire path. Right? Because there won't be any contention. Is that clear? So basically it means, so we set a dedicated path for a given communication. Right? So there won't be any contention during the route. right? So we do not need the buffer to temporarily store the packet or to store the data. Am I right? And the packet switching is routed per packet in each router, right? So route each packet individually. So they may have some contention. That's the reason why we need some buffer to temporarily store the data. Is that clear? So this is the key difference between the circuit switching and the packet switching, right? But the problem for the circuit switching, we need to set up and bring down the path, which will take time. Right? Every time we need to take some time to set up the path and disconnect the path and reset another path. For this one, we do not have to set up, so we directly inject the packets into the network, right? But the problem is what? Problem is we need to implement an additional buffer to avoid this kind of contention. Right? Is that clear? So if we reserve something for the communication, so we do not have to temporarily to buffer them. Right? We can directly open a path between the source and destination. Right? So we do not have to temporarily store the packets. Right? For this one, we just keep injecting the packets into the network. Right? They may have some contention, which will be handled by the flow control or routing algorithms. Right? But we need to provide some temporary storage, right, to avoid the contention. Right? Is that clear? And the routing mechanism, okay, so there are multiple ways to do the routing. The first one is arithmetic, right? So simple arithmetic to determine the route in the regular topology, dimension order routing or in mesh or torus. Right? So basically, it's quite easy to calculate. So you go which direction based on this, based on some simple direction. The second one is source-based, right? So which means source specifies the output and for each switch in the route. Simple switches, no control states, larger header. So what does this mean? So which means at the source, we pre-compute, right, the route. So basically, I will include some information in the packet. So say, okay, which direction, which router you should go in the first step, and which router you should do for the second and third until the destination, right? So in such a case, you need to have the entire topology information, and you also know what is your source and what's your destination, and then you can pre-compute entire path and embed this kind of information in the packets. So this means we have a larger header, right? Because you need to put additional information into the packets, which will occupy some space. Right, but for this one, it's all arithmetics. You just compute some destination at runtime because you know which dimension you should go. Right, just simple calculation. Right, the dimension and your current. So the last one is table lookup based. So index into the table for output, smaller header, more complex switches. So basically it means you have a table to record. So what's your destination and what's your current location, right? So it will look up an entire table and to let you know. So what would be the next stop? Right? So why we need to do the table lookup based? So probably it's reconfigurable. Sometimes you can change the contents in the table, right? And this provides you a scalable way to change your routing policies. But for the arithmetic one, so you cannot do anything for that. Once you implement this kind of logics in the hardware, you cannot do anything for it. Right? Source-based is also, you can update that sometimes, right? But the thing is, the information will occupy lots of the header information. For this one is each router will sacrifice some storage, I mean the additional logic to store the lookup table. Is that clear? So the differences between these two ones, we give the overheads to different components to achieve the same goal. right? Either we can let each packet to record their route information, right? Or we implement some table in each router, right? You have these packets and you have this router. Basically, two key components. Right? Different ways to do that. Is that clear? So routing algorithm, the other angle of visiting the routing algorithm, right? So the previous one we mentioned is what? So different ways to implement, right? But for this one is what? The algorithm side, algorithm-wise, we have three types of deterministic, oblivious, and adaptive. So the deterministic means always choose the same path for a communicating source-destination pair. So there is only one way to go. Right? It's predetermined, so you cannot change that. There is only one path between a pair of the source and destination, right? You cannot change that. So oblivious choose different paths without considering the network state, which means you can do some selection, random selection. For example, I can do random, right? I can randomly pick up one direction to go, right? Without considering the network states, which means we only just implement a policy, right? To give the possibility of selecting different directions, right? Adaptive means we choose a different path, adapting to the state of the network. For example, if we have 4 ways to go, right? Like Google Map, but the map provides.
That's the element of work in this scenario. I kind of choose like the shortest path. You know, I don't know if this applies in this scenario, but I was looking at Netflix Plus, where you have, let's say, like a 2D array, and then you use that one algorithm to kind of determine the shortest path between like certain connections. Does that work in the scenario or
It depends. It depends. Very good questions. Very good questions. So on these kinds of the routing algorithms actually have different performance, right? In different, traffic patterns. Right? So that's the reason why people are proposing different kinds of routing algorithms. It highly depends on the traffic patterns. So I probably can give you some examples later to show you which one is best for which kind of the situations. Okay. And adaptive means, so we need to consider network status. So which basically means if a certain route, or the route is has very heavy traffic, so probably we need to avoid that, right? To select the idle one, right? This is adaptive. So we are adapting to the state of the network, right? So of course we need to implement additional, hardware to monitor the network status, right? So this is the cost. So how to adapt, like I mentioned, the local global feedback. So basically you can just monitor the local traffic or the network status for different ports, right? And then you can select. Right. For the global, so probably you need to gather the information from different components, from different locations, and to determine which one should be the best. Like the Google Map. The Google Map actually is collecting the data from different customers, right? And there is a central controller to make this decision and to provide some feedback to you. But it's impossible for the chip, right? So the Google Map, the algorithm of the Google Map is supported by hundreds of the data centers or servers, right? Collecting, billions of the data, collecting data from billions of users. It's impossible for a chip design, right? Sometimes this would be a concern for us, right? And a minimum or non-minimum passes, right? So we either select the minimum or non-minimum. It highly depends. Right. Sometimes the minimum pass is the best way, but sometimes it's not. Right. So probably I will give you some examples. After next week probably to go over them. Right. So what would be the best selection for different application. So deterministic all packets between the same pair take the same path, dimensional order routing, right? We can either go through the X direction or Y direction if we consider two-dimensional topologies, right? Simple, deadlock-free, and could lead to high contention. So probably I will also go over the deadlock concept next week to let you know. So what is deadlock, so that you can enter these type of questions. Okay. So I believe is one, balance the network. I will randomly choose an intermediate decision, route it first, then route from there to the destination. Right? So the randomness can somehow balance the network load, but it's not the minimum path. Right? So optimization do this on high load, restrict the intermediate node to be closed. So adaptive routing is same. The minimum, we can do the minimum or do the non-minimum adaptive routing. Right? So by monitoring the status of the network. And that's all for today, okay? So I'm still collecting the problems for the second project, okay? So this Wednesday, I will probably go over the project 2, right? So probably I can also open a terminal to show how to utilize some commands, Linux commands, or how do we compile the simple scalar, right? And how to debug. So I'm still collecting the common questions from you. So you can send these types of questions to me by probably by Tuesday, okay? So that I can have enough time to prepare the slides. And then next week, I will go over some examples, running examples for explaining different kinds of the routing algorithms and how do we analyze the bandwidth latency, right? In different traffic patterns, right? So then we will, the rest 2 lectures for the review before before the final, right? Because December 3rd is the last day of the class, right? The end of this, if I remember correctly, right? So basically, we only have 3 or 4 lectures left for this semester, right? And this Wednesday, I will give you the homework 4, right? And I will collect the homework 4 by next Wednesday, probably it's just before the Thanksgiving, right? And then we will go over all of these homework problems in the review sections, right? Because we have some delay in the homeworks because the deadline was supposed to be last Wednesday, right? Or last Friday. So we have some delays. Extend the deadline a little bit. So that's the reason why we have some delays.
So what days do we have class next week? We don't have class.
Next week, let me check. Okay, so I'm not sure if we have class or not. So next, I believe we will have a class next Monday, I believe, right? Because the holiday will start from next Wednesday, right? So we will have no class on next Wednesday, but we will have 1 class on next Monday.
And then the 29th, we review.
Yeah, 29 we will have a review. December 1st we have a review, second review, and then that's all for this semester.
And then we do our final on
The final on December 8th,
okay.
right?
Projects due on the 10th.
Yeah. So we are approaching to the end of this semester, and probably it's time to say goodbye on the December 8th, right?
Homework will be due on 4.
Homework 4 will be due. Probably can you submit by probably next Wednesday, 24th, or you can submit it 23rd. Is that okay?
Yeah. How many problems are going to be on problem 4 for homework?
3 or 4? Yeah, 3 or 4.
And it'll cover the routing.
No. It's just for the pipeline. So for the interconnection, I think it is not covered in the course description. I think it's, some. Okay. Right. And then we will have final. Remember that in the final, we have more questions as comparing, comparing to the midterm, because midterm we only have 90 minutes, right? For the final, we have 2 hours and 30 minutes. So probably we will cover more questions.
You said the final was not cumulative, right?
Yeah, not cumulative. Yeah. But we'll cover, the cache coherence might be, okay, all the homework problems from the homework 3 and 4. Similar questions, okay? Just relax. And so homework 4 is due next week. And the week after next week is the review week. Yes. So you're right. So November 29th and December 1st will be the review for homework 3 and 4 with all this information. Yes, I will send an announcement with all this information. That okay? Any other questions? No questions. I think we can end today. Okay. See you Wednesday.